From this point on, 3 lectures will be devoted to the very important topic of network science, community detection. So the community detection is a very pragmatic issue in network science for its wide and far-reaching applications, as well as its roles in fundamental network science. Before we start technical discussions, let's briefly look at a piece of recent history of the Kingdom of Belgium. Belgium is often viewed as a prototype of a society that has found a way for 2 cultures to peacefully coexist for centuries without one culture absorbing or dominating the other. Indeed, the country is bilingual. 59% of its citizens call themselves Flemish, speaking Dutch. The other 40% are Walloons and speak French. Belgium is of approximately the same size as Gyeongsangnam-do, Gyeongsangbuk-do combined, but its population, 11 to 12 million, is slightly less than that of the 2 Korean provinces. Geographically, ethnically, and the country can be divided into 3 regions, actually. Flanders at north, Wallonia at south, and Brussels capital region. The people of the southern provinces from then the United Kingdom of the Netherlands were mainly Flemings and Walloons. Both people were traditionally Roman Catholic, as contrasted with Protestant-dominated people of the north. And there were high levels of unemployment and industrial unrest among the working classes, which led to Belgian Revolution in 1830 and eventually created the Kingdom of Belgium. So, do their 2 ethnic groups live in a society that is so smoothly knitted together that no one notices who is Flemish and who is Walloon? Or is Belgium 2 countries within the same borders? That is to say, 2 societies live side by side, minimizing the interactions and thus potential points of friction between the 2 ethnic groups? There is an anecdotal evidence for both. Hence, the answer depends on whom you ask. It was impossible to offer an unbiased answer to this question until network science came along. In 2008, in the Journal of Statistical Mechanics, Vincent Blondel and his students have started applying a new community finding algorithm to the call patterns of one of the largest mobile phone operators in Belgium. It was originally designed to identify groups of individuals who regularly talk with each other on the phone, breaking the whole country into numerous small and not so small communities by placing individuals next to their friends, family members, colleagues, neighbors, and everyone whom they regularly called on their mobile phones. The result was somewhat unexpected. It indicates the Belgium is broken into 2 huge communities, each consisting of many smaller circles of friends. Within each of these groups, the communities had multiple links to each other, yet these communities never talked with the communities in the other group. Between these 2 big groups, there was a third, a much smaller group of communities sandwiched, apparently mediating the 2 parts of Belgium. So the question to be addressed throughout this lecture will include the first, the definitions of community. What is community in the sense of network science? And fundamental hypotheses underlying all these community detection algorithms. And we will explore some technical details on the graph partitioning and hierarchical clustering and so on. So after taking these lectures, you should be familiar with the concept of modularity and its optimization. And also, you should be able to write code to detect the community structure for a given network. Okay, let me start with this celebrated Zakari's Karate Club network. By community here, we mean a group of nodes that have a higher affinity, proximity, or similarity to connect to each other than to nodes from other communities. So in this example of karate club, individuals, people are subdivided into two groups who supports the president or the instructor of the karate club. So the original publication was made back in 1977, almost a half a century ago. And after that, the citation history shows a very abrupt increase around 30 years after the original publication. And also, there is a so-called Karate Club Prize. It is awarded to the first scientist at any conference on the networks who uses Zakari's Karate Club as an example of his or her method. And those recipients are inducted into the Zakari's Karate Club and awarded a small trophy prize like this. All right. The emergence of systems biology or network biology at the dawn of millennium was driven by the increasing awareness that an ultimate understanding of how the cell works requires a detailed understanding of the underlying cellular networks. Communities play a special role in this context, helping us understand how specific cellular functions are encoded in the cellular network. This was emphasized by Lee Hartwell in 1999, 2 years before he received his Nobel Prize in Medicine, together with John Hoffield, Stan Leibler, Andrew Murray, in a paper titled From Molecular to Modular Cell Biology. They argue that biology must move beyond the single molecule approach and focus on groups of molecules involved in the same cellular functions, calling them modules. Such modules were first identified in the cellular metabolism of E. coli by Ravas and collaborators, who developed an algorithm to identify groups of molecules that, based on the patterns of the reactions that connect them, form detectable communities. The algorithms not only recovered some of the biochemically distinct molecules of bacterial metabolism, but has started an avalanche of research within the system biology on the community structure of cellular networks. An example is provided here in this picture, which shows the genetic network within yeast, highlighting the community structures for specific cellular functions. On the right, the topological overlap matrix of E. coli metabolism and the corresponding hierarchical tree that helped identify the modules are shown. The technical details we will shortly follow. The color of the branches reflect the predominant biochemical role of the participating molecules, like carbohydrate in dark blue, and nucleotide and nucleic acid metabolism in red, right, and the lipid metabolism colored in cyan. So the red right branch of the hierarchical tree, highlighting the region corresponding to the pyrimidine module is actually the predicted community by the Rava's algorithm. If we zoom in this sub-branches, then we see the metabolic reactions within the pyramid module. The boxes around the reactions show the communities predicted by the same algorithm. As emphasized by the previous pioneering works in systems biology and network biology, we should see the forest instead of trees. The network biology is an effort to see the forest. Instead of focusing on individual components, we can reach the understanding of the living system only when we see the whole. For this purpose, community detection is quite an essential tool and an important conceptual framework as well. So unlike the man-made electronic circuits, cellular reactions occurring inside a cell has no isolated conduit or isolated channel of chemical reactions. Everything that can take place would happen, interfering one another. That's the main difficulty when quantitative physical scientists wanted to understand the living system as a whole. So we would speak about the limitations of reductionism, but how do we get over it? So that's a very long-standing puzzle when the biology try to be quantitative. So there is a long history regarding this community finding algorithms, well described in our textbook. So please go ahead and enjoy your reading. And now I'd like to talk the technical details underlying this community detections. So before the main details, we introduce the main hypothesis underlying all these stories. So as we have seen in Belgian cell phone networks and Zakaria's Karate Club, there are well-defined, or at least reasonably defined, communities inside a network that can be captured as a subnetwork or subgraph. And the notion of community is actually rooted in who or which component connects to which other. Okay, so which cannot be explained based on what the degree distribution itself. Okay, so PK is simply about how many connections an individual node has. Is right? So we must inspect a network's detailed wiring diagram. Who is connected to whom, or which component is somehow affiliated which else. So that information is contained in the adjacency matrix Aij. So that goes with a fundamental hypothesis H1, saying a network's community structure is uniquely encoded its adjacency matrix, basically. Okay, and the second hypothesis we are based on is the connectedness and the density hypothesis, which says a community in a network corresponds to a connected subgraph, and the community is corresponding to locally dense neighborhood of a network. Okay, so the community, by definition, is a densely connected local subgraph, which is relatively rare or just a few connections with the nodes outside that community, right? As a specific realization of community, here is the K-click. Clique is a complete subgraph of K nodes. That means the nodes belonging to K clique, they are all connected completely. So they are complete subgraph. While the connection between this K clique and the nodes outside this clique is just rare, relatively rare. Okay, so 2 cliques, 3 cliques, and 4 cliques, and so on, higher cliques you can think of, but in reality, only the 2 cliques will take place with finite probability, especially when the network size becomes very large. As we raise the number k, the realization of higher clique is pretty rare. And also finding the cliques in a network is computationally very, very demanding. So it's NP complete problem. So expected number of k-clique for Erdős-Renyi type random network with n nodes and linking probability p is given like this. So the first factor, choose k out of n, is trivial, right? And the second term, p to the power of, the combination, choosing 2 out of k, is also simple, easy to understand, because the exponent here is the number of links in a complete subgraph of k nodes, right? So choose 2 out of k clique members. Okay, that's the meaning of the exponent here. And finally, the third term is saying that the other nodes that are not contained, included in the k clique, which is n minus k many, right? So these out of clique nodes should not be connected to all the members of the k clique. So this is not all statement. Okay, so if you carefully look at this exponent n minus k, this refers to the number of nodes that don't belong to the k clique. And 1 minus p to the kth power, that means it's the probability of the complementary event, right? So the other node, which is not part of the k clique, that should not be connected to all of the member node in the k clique. So that is the meaning of inside this parenthesis. All right, and then we move on to define the strong and weak communities. Once the community is assigned, then we can define this internal and external degree of individual nodes. Internal, by definition, is the set of edges of a node I that connects to other nodes of the same community. So literally, it's internal. Likewise, external degree can be counted as the number of links emanating from individual node I that connects to the outside of the community, right? So if you look at the sample network on the right top side, here we already assigned each node to 3 communities. So the 5 top right nodes are assigned to orange community, and the lower left green nodes are assigned to green community, while the middle node is assigned to the gray community. So if you focus on the 2 edge nodes of orange community and green community, all of the 4 nodes have the internal degree 3, right? If you carefully count the number of edges that go to the members of the same community, that is number 3, right? And the external degree is just 1, because all of them, 4 of them are connected to the gray node, which is outside their own community, right? So in this way, you can define the internal and external degree. And based on these numbers, we can tell the community is strong or weak or moderate, you can say that. So the criterion here is pretty natural. If the external degree is 0, all neighbors of I belong to its own community C. Then C is a good community for individual node I, right? That's pretty natural. Likewise, if internal degrees is 0, all neighbors of I belong to other communities, then I should be assigned to a different community, right? And if you focus on the orange node on the lower panel, then these 4 nodes constitute a 4-click, right? So all of the 4 nodes are connected one another. It's a complete subgraph, while no nodes outside this community is connected to all of the 4 nodes, right? So that complies with our previous definition of K-click. And the second one, if we assign the 5 top right nodes to a purple community, then this community is pretty strong in a sense that the nodes belonging to this community, all of them has higher internal degree than the external degree, right? So that is the definition of strong community. On the other hand, if you include the middle one, the previously gray node, as a member of a new community, now the community is made up of 6 nodes, then this is going to be weak community. Why? Because the sum of the internal degree is higher than the sum of the external degree. But not all the nodes belonging to this green community satisfies the criteria, which is internal degree being higher than the external degree, right? So individually, they may not satisfy the good community criterion, but as a sum, the internal degree is higher than the external degree. That is okay to define the weak community. All right, so far the discussion sounds pretty intuitive, but now we try to extend our discussion for general-sized networks, which has many components, many individual nodes. So the question goes, how many ways can we partition a network into 2 groups? Okay, so-called a graph bisection problem is we want to divide a network of size n into 2 equal non-overlapping subgraph of size n half, right? N halves. So according to our high school mathematics calculation, yes, the number of ways can be written down like this. Here, we try to be general by introducing n1 instead of 1 n halves. So the factor is now approximated using the so-called Stirling's approximation scheme. To be rigorous, Stirling's approximation refers to this prefactor, square root of 2 pi n, but yeah, that's not so relevant in this derivation. So if we use this approximation scheme, then we come up with the mathematical expression of 2 to the power of n plus 1 and divide by the square root of n, right? So in other words, the amount of computational time required to inspect all divisions increases exponentially with the size of the network. To illustrate the consequences of this conclusion, if you consider a network with just 10 nodes, then 10 factorial divided by 5 factorial squared gives us just 252, reasonably small number of ways that can be performed by modern-day computer within 1 millisecond. But if you chose a network composed of 100 nodes, it already surpasses a huge number, which is 10 to the power 29th power, right? So it's already a formidable task, even if we use the supercomputer of modern days, right? So you can imagine how formidable the task will be if you want to explore all the possibilities of bisecting the network of an integrated circuit, which is composed of over 1 billion transistors, right? Now, let me introduce the Kernighan-Lin algorithm. Okay, the best-known algorithm for graph bisection was proposed by Brian Kernighan and Shan Lin in 1970. By the way, Kernighan is an author of the C programming language with C creator Dennis Rich, the first book on C. I learned the language C using his book when I was a college student. Okay, the algorithm goes like this. So we start with a random partition of a network into two groups, okay? And it doesn't matter which partition we chose at initial stage. So if we pick up a random pair of nodes, ij, from each of the groups, then swap their affiliations, okay? And then record the resulting change in the cut size. Cut size is defined as the number of links between the two groups. And by testing all ij pairs, we identify the pair that results in the largest reduction of the cut sizes. For example, in this sample network, by swapping this purple and green node with orange peripheral lines, we could reduce the cut size from 6 to 2. So it is accepted move. Okay. One non-trivial part of this algorithm is, in case no pair reduces the cut size, we can swap the pair that increases the cut size the least. Okay. Yeah. And by iterating the above process until each node is moved once, that completes the Kernighan-Lin algorithm. And you can find wide variety of applications of Kernighan-Lin algorithm. To name a few, we can use this algorithm for simplifying the process of chip design, where the engineers partition the wiring diagram of IC, integrated circuits, into the subgraphs. Also, we can utilize this algorithm for partitioning a large computational problem into subtasks and assign them to individual processors. Minimizing the cut size in both cases is critical because the communication between different units, different processors are usually the bottleneck, right? But you may already have noticed that there was a missing point. The previous arguments are based on the predefined number and size of the communities, which are never trivial from the beginning, okay? Actually, the number of possible partitions for a graph with n nodes, called Bell number, grows exponentially as the network size n. So for most of the practical situations where the number of nodes exceed several thousand, if not million, it is simply impossible to enumerate all the possibilities. So we need novel protocols that do not require this full inspection of possibilities. All right? Is it impossible, by the way, or is there any smart way to work around this difficulty? Having said that, I have to stop here, and we will meet at Wednesday class, starting with this hierarchical clustering.